We are going to use the theorem in the previous video to help us solve a system of linear differential equations that has three equations. Here's what we're going to solve. Now it's a bit of a long problem. I'm going to tell you all the answers. I'm going to do some of the algebra, but I'm going to leave a few gaps in it for you to fill in the details. Okay, we got three equations. X prime is 2x minus y prime is this, and z prime is this. Notice I lined them up nicely, so you have the x's and the y's and the z's lined up. So we've got a function of x, y, and z here, even though it's just plus 0z. A function of x, y, z here, and a function of x, y, z here. First, we want to write it like we would, using a matrix notation, so we can end up solving it using the previous theorem. This is the equation. This is the three equations. X prime is nothing but the column vector, x prime, y prime, z prime. This is our coefficient matrix. I usually call that capital A. Came from 2, negative 7, 0, 5, 10, 4. The coefficients, 0, 5, 2. X is our solution. That's what we're looking for. X is little y, little x, little y, little z. It's just a column vector. Okay, so we have our system that we're trying to solve. Now recall from the theorem that the eigenvalues, which we need, remember the eigenvalues, those lambdas, they're part of the solution. We need to find those. And we find them by solving this equation. And I know this doesn't look much like a polynomial, but it is a polynomial, and it has lambdas in it. And so we're going to have to solve this and find the lambdas that would essentially be the solutions to this equation. So, the determinant of A minus lambda I. Remember, A is right here. Lambda I is the identity matrix times lambda. So, it's all zeros with lambdas down the diagonal. So, this left-hand side is equal to, and notice this looks, most of the terms are exactly this, A. But in subtracting this only on the diagonal terms, everywhere else we're subtracting 0. So on the diagonal terms, you just put 2 minus lambda, 10 minus lambda, 2 minus lambda. Other than that, it looks just like the matrix A. And then we're taking the determinant of it, and just as a reminder, we'll set it equal to 0 in the end. Right here. All right, so to review how we get the determinant of this 3 by 3 matrix. We're going to go across the top row. You could go across any row you wanted to, or actually any column. I usually go across the top row, and in this case especially because there's a 0 in the top row, it just makes the arithmetic a little bit more simple. I'm going to take this 2 minus lambda, and I'm going to multiply it by the minor, is what it's called. The minor, that cofactor, is almost the same thing. The minor of this one element it's the determinant of the matrix obtained from removing its row and its column. So it's going to be 2 minus lambda times the determinant, that 2 by 2 determinant. So I've got 2 minus lambda times this determinant, right there. Then I'm moving across. And so you can see the coefficients go 2 minus lambda, negative 7, 0. Well, you start off with changing every other one to be a negative. So it's a plus 7 because we take this one just as it is, we take the opposite of this one, and we take this one just as it is. And then the second term, negative 7, which became a positive 7, remove the top row, middle column, and we're left with 5, 4, 0, 2 minus lambda. And so this term's cofactor is this determinant. And then 0, I went ahead and wrote it out, even though we're going to get a 0 here. The cofactor associated with that term 0 is the determinant of that 2 by 2. So now we know the determinant of a 2 by 2 is simply the product of the diagonal minus the product of that reverse diagonal, or opposite diagonal, the other diagonal. So this is equal to 2 minus lambda times, maybe we'll use brackets, 10 minus lambda times 2 minus lambda. Minus 5 times 4 is minus 20. So that's the first term. And the second term is plus 7 times 5 times 2 minus lambda minus 0. I'll go ahead and put minus 0. So you can see that when we FOIL this out and subtract 20, we get a lambda squared. Over here we have another lambda, so we're going to end up with a cubic polynomial. And to save a little bit of space, I'm going to write down, after we do all of this algebra, we end up with negative lambda cubed plus 14 lambda squared minus 59 lambda plus 70. And we have to set that equal to 0. So if you wanted to, you could call this determinant, if you wanted to, you could call it f of lambda, because it's a function of lambda, and we're setting it equal to 0. Okay, so this is going to be a refresher from pre-cal. We need to factor this. If you can factor that in your head, you are a good factorer. The first thing we need to do is just find one single 0, one root, one lambda that works. And then we'll do synthetic division, and after we divide, we'll get a lambda squared, a quadratic, which everybody knows how to factor, I think. So, going back to pre-calculus, when you have a polynomial set equal to 0, the only rational numbers that could possibly be zeros are all of the factors of this number divided by all of the factors of this number, the coefficient, this coefficient, the constant term divided by the leading coefficient, divided by the leading coefficient. The factors of this over the factors of this. Since this is a 1 or a negative 1, we're not going to have any fractions, so that's nice. And you can take plus or minus all of those. So for us, since the denominator is going to be 1 or negative 1, we get the possible rational zeros are 1, because that's a factor of 70, plus or minus 2. 3 doesn't work, 4 doesn't work, 5 works. Plus or minus 5, plus or minus 7, plus or minus 10, plus or minus 14, plus or minus... do I jump up to 35 already? Let me see if I've got this. Yeah, 35 plus or minus 70. Hopefully I didn't miss any. That looks about right. So normally in the problems I use, and after we try a couple of these low numbers, we're going to find the first 0. So we start with the easy ones. And I think at this point I will pick it up on the next board. We need to find out one, for starters, 1 0, which will give us one eigenvalue, one lambda. Okay, so here I called it f of lambda. Here's our characteristic polynomial. We use the factor theorem, and I've already done some work for us. F of 1 failed. F of 1 is negative 1 plus 14 minus 59 plus 70, and that is not 0. F of negative 1 failed as well. F of 2 is this. There we go. F of 2 equals 0 means that lambda minus 2 is a factor of this polynomial. And therefore lambda equals 2 will be one of the eigenvalues. So lambda minus 2 is one of the factors. So now I need to continue factoring. This polynomial is lambda minus 2 times another polynomial. We can divide it out now and it'll go evenly. So using synthetic division, since f of 2 is 0, I'm going to put I'm going to put 2 in the cup. And I'm going to put the coefficients of, let's see, -1, 14, -59, 70. And when I do the synthetic division, I ended up with the remainder of 0, which was totally expected. If I got something different, it means I made a mistake, because I know that lambda 2 is a factor of this polynomial. So this gives us that, oh, looks like I worked all of the polynomials out. So now we know f of lambda is equal to lambda minus 2 times this polynomial, where this is that times lambda squared times lambda, and that's the constant term. Well, I decided to factor out a -1 and make it positive lambda squared minus 12 plus 35, because it's easier to factor when lambda squared is positive. And that factors into x minus 5, a lambda minus 5, lambda minus 7. So we've got our eigenvalues. Those 3 numbers are going to show up in the solution. What else did we need? We need to find k1, k2, k3 eigenvectors that correspond to lambda 1, lambda 2, lambda 3. So we're going to set up the equation for, let's start off with lambda 1. For lambda 1 equals 2, we're going to get the equation a k1 equals lambda 1 k1. Yeah. So that's the equation we're going to use to solve, to find out what k is. Now, I think I did this in a previous video, but that means that, maybe I'll go to the right one more time, save some room down here. That means that a k1 minus lambda 1 k1 equals 0. And that's the 0 vector. So from here, we say that a minus lambda I times k1, I'm factoring the k1 out, and we have a minus lambda 1, but they're different terms. This is a column vector, this is a square matrix, so I multiply this by the identity matrix. Now these are both square matrices of the same size, so we can subtract them. Oh, actually, we know what lambda 1 is. So we get a minus lambda 1 is 2. 2i equals k1. All right, let's figure this out. What is a minus 2i? Well, I'll go ahead and write it down. What was matrix A? The matrix A was 2, -7, 0, 5, 10, 4, 0, 5, 2, minus lambda I. Well, that's easy. That's just 2, 2, 2 down the diagonal. So this is just 2 times I. So that is equal to our k1, our eigenvector. And so maybe I'll just write that down. And now let's combine this. So we get 0, -7, 0. I'm doing term by term subtraction. 5 minus 0 is a 5, 10 minus 2 is an 8, 4 minus 0 is a 4, 0 minus 0 is a 0, 5 minus 0 is a 5, 2 minus 2 is a 0. So that is equal to, let's see, that, maybe I said that wrong, didn't I? This is this. This times k1 is equal to 0. So to find this vector, we could call it whatever we want to, u1, u2, u3. we're simply going to solve using basically our linear algebra. We will set up (0, -7, 0, 5, 8, 4, 0, 5, 0, and we're going to augment it with 0. We'll find, and that'll give us K1. That's going to be exactly what we're looking for. Did I make a mistake? I got -7. In my notes, I've got a +7, but I think -7 is correct. Yeah, I think this looks right. All right, so how are we going to solve that? Well, it's actually fairly easy. We'll go ahead and do the Gaussian elimination to do it. So I will proceed here. I'm running out of room already. I'm going to switch rows. I need to have a non-zero number here. So 5, 8, 4, 0. Then I'll put the -7 on the next row. 0, -7, 0, 0, 0, 5, 0, 0. Well, you probably remember that you are allowed to multiply any row by anything you want to. I'm not going to go through every row operation. I could multiply this by something 5/7 and add it into this one and make that a 0. I could divide this row by -7 and I make that a 1. And then do I need to? I probably don't need to, but I'm going to go ahead and divide row 1 by 5. So what I did was divided row 2 by -7, and I did a row operation that added some multiple of this row into this one and making that a 0 row. So then we get 1, 8/5, 4/5, 0. And then 0, 1, 0, 0, and 0, 0, 0, 0. All right, so what's next? What does row 2 tell us? Row 2 tells us that, let me refer to the elements of this vector as little k1, little k2, little k3. The elements of this big capital K1. That tells us that K2 is 0, because 0 times K1 plus 1 times K2 plus 0 times K3 is 0. So we get that K2 is equal to 0. So in back substitution, if that's a 0, we're going to get, for this row 1 is going to give us that K1 plus 8/5 times 0. I'll go ahead and write that down, even though it's 0, plus 4/5 times K3 is equal to 0. So that gives us that this is 0. K1 is equal to -4/5 K3. Just subtracting it. Okay, so just to make it nice, I'm going to try to get integers out of this. Remember, there's an infinite number of vectors that will work, okay, for this one, lambda 1 equal 2. Let's pick one that's nice, maybe one that doesn't have any fractions in it. So if I were to choose, I know K2 is 0. We have to choose a value, that's K1, for either K1 or K3. If I choose K3 to be 5, that's going to be nice, because we get K1 being a -4. So choose K3 equal to 5. And that gives us K1 equals negative 4/5 times 5 is negative 4. So, capital K1 is, K1 was negative 4, K2 was a 0, K3 was 5. Put a box around that. And I've pretty much ran out of room, so I think what I'm going to say here is that lambda 2 was 5. Maybe I'll start with a different color here. Lambda 2 equal 5 implies that a minus 5 lambda, 5i, K2 equals 0. You do all this type of algebra that we did, and that gives us that K2 equals negative 7, 3, 5. And it's possible you'll come up with a different vector than that, a multiple of it maybe. I just chose one that gave me nice integers for answers. You could get, end up with one that's, for example, in this one, we could have said K3 is a 1. K2 is 0, K3 a 1 would make K1 negative 4/5. So there's an infinite number of possibilities. All right, so lambda 2 is 5, K2 is that. Lambda 3, we got 7. I believe it was 7. Yep. And for that, we get a minus 7i K3 equals 0. And doing this bit of arithmetic gives us K3 equal to the vector 7, 5, 5. All right, and I don't want to write the final general solution too low here, so I'm going to write it right in here. Solution. This is the general solution that we were looking for. X is equal to a constant times K1, which for us is negative 4, 0, 5, e to the lambda, which was 2t, plus C2 times K2, negative 735, e to the lambda 2, 5t, plus C3 times K3, which is 755, e to the lambda 3t, and lambda 3 is 7. Oops, 7t. So not difficult, just quite a bit of algebra required to come up with a general solution. So this is going to be a good review, hopefully review for you in computing eigenvalues and their associated eigenvectors, because they're part of the general solution. So if you've had linear algebra, this is review. If not, you're getting a head start on in the future when you take linear algebra.